Great, thank you very much. Well, pleased we're scheduled this way around. So obviously we have a CHERI Alliance. We're trying to get the technology out there. But CHERI is a portable model. We can target it at different hardware. But one of the key things about CHERI is it's basically, we need both hardware and software working in unison to really extract the security benefits. You can't have CHERI without CHERI-enabled hardware. And as was pointed out by Gavin, hardware just takes more effort. Once you've shipped it, you can't just patch it trivially. And so it does require more effort. There is more cost involved than shipping software. That said, the breadth of software we use today, also there's vast amount of engineering effort. So there are very significant costs in porting systems onto CHERI as well, although we've made that as easy as possible. Anyway, today I'm going to really focus on that interface between hardware and software, and referred to as instruction set architectures, ISAs. And the top ones commercially today are ARM. If you've got a mobile phone, you'll undoubtedly have ARM processors in it. And ARM is headquartered in Cambridge, and I'm in Cambridge, and that's jolly convenient. So we've worked with ARM extensively on the Digital Security by Design initiative. We have done a bit of a sketch for Intel AMD's x86, but actually our focus has been on RISC-V, originally MIPS for our very early research. The focus has really been around the proprietary ISA ARM. So ARM controls that instruction set architecture. It is a commercial instruction set architecture. They have a set of partners, and which is interesting. So it's not just them providing IP. That there are ARM architecture licensees, and so it is a club, but it is a closed club. And that's one way in which you commercially build hardware. And then the other one, which is to some extent a little bit more recent, really, is actually working on more open source components. So it's great to hear from Gavin from Low Risk explaining that. And RISC-V has a lot of momentum at the moment in the open source hardware space. But it's also, from a research point of view, an area we can play in because we're allowed to. As I don't have an ARM architecture licensee, so I can't build my own ARM processors, but I can, within my team, build CHERI enhanced RISC-V cores. Okay, ARM Morello, though, has been hugely beneficial for the Digital Security by Design program. It's provided this base hardware platform. It's a high-end platform. Had lots of companies engaging with it. We've seen swathes of software run on it. People have seen the benefits, and this is all great. And most of those companies are now saying, well, where's the hardware? We want the commercial version of the hardware, because Morello is very much a prototype. And that's really probably the biggest challenge we've got at the moment with CHERI, is to get a lot of commercial hardware out there that people can buy and deploy. And one of the problems is in the high-end space, ARM does small cores, but they also do high-end cores for phones, but also servers. There is just a lot of engineering effort. And to do a new processor design, you're typically talking about 4 years of effort. And ARM says, well, we're just waiting for a customer who will buy 100 million units, and then we'll do it. So it's got to be one of the big markets, because that's, so if you land it in a mobile phone, if Google or an Apple come out and say, we want to add CHERI, it can happen. But it is a bit of a challenge. However, one thing we can do is look on the smaller end, where it's much easier to deploy and where the costs of development, simpler cores, older silicon technology typically, it's much easier to get things out of the door. And that's really where we're seeing a lot of the activity today, including various people represented here. So, Codasip's here, SCI, Semi's here, Low Risk are here, and they've all got, medium to small cores based around RISC-V. And this is just marvellous to see because it's a great starting point. It allows a broader range of industry to gain expertise and confidence in using CHERI, and I think makes it easier to make big decisions to deploy at scale on high-end systems. There's also still clearly an awful lot that's confidential. I mean, there's a few things coming out of Google, but I'm hoping there will be other things in the next year or so. And we see other companies engaging, but have not really talked very publicly. And I realise I was talking to Angus earlier from Sequoia, who we've been working with a bit, and I forgot to mention on here, and I was trying to remember how much is public, but you're here when you're talking about things, and that's good. To actually get CHERI out into this open standard, RISC-V, is a challenge that I've been grappling with various people, including Alex Richardson at Google. We're sort of chair and co-chair of the CHERI task group to do the standardisation. We've done a huge amount of work, particularly with Codasip. I have to say they've been brilliant to work with, great group of people, put an awful lot of time and effort in. And we now have a spec which is, 98, 99% complete. We have a roadmap with RISC-V International to take that through to standardisation. And that's really important because, this interface is the interface between hardware and software. We want lots of people to be able to port software to run software on CHERI RISC-V machines, but they want it to run on every CHERI RISC-V machine. Similarly, the hardware people want to build something that is going to be compatible with any CHERI RISC-V software that's out there. So, getting this interface standardized is really very critical. Let's just say at a very high level, because we're running a bit short of time, just give you a hint at some of the things that are in this standard. One of the things we've done is taken a lot of lessons from the Morello work and basically down-selected. Basically, Morello had quite a few options, different ways of doing things, because it was an experimental platform. And that was hugely helpful because we've been able to port large software stacks and really learn what things were good and what things perhaps we don't need, or perhaps we're too complicated and we could do something simpler. Anyway, at the heart of CHERI is the capability, which is this bounds check pointer with permissions that various people have been talking about. So we have to add that. That extends integer registers. We then add a few instructions, and it's actually not very much. One of the things, if you're trying to standardize something like this, is actually how much of the encoding space for the instruction set. So low-level details, but it's actually rather important how much, if you're going to add an extension, do you use, because it's a finite resource. And we've been able to keep this down actually to a lot of what are called R-type instructions, so register to register, and two operand instructions that are all very easy to sneak into little corners where there are holes in the encoding space. So it doesn't really use much space at all. And we only have one instruction that has an immediate called cadd. And this has been actually quite critical to sort out to make it acceptable to go through this standardization effort. We also extend what the load and store operations, so we've added a mode bit, so if you're in capability mode, load and store operations basically checks bounds and permissions and so on. And that's also useful because it means we load and store instructions use swathes of the encoding space, so you don't want to introduce more of them. And for completeness, there's other things around page tables and status registers and other things. So let me wrap up. So CHERI is a portable security model. It can be applied to any commercial microprocessor. But actually, one of the things I hadn't said already, it's one of those things you can't really do this as a startup with a new processor. because basically nobody's interested. You know, the tool chains, the big tool chains, all the software support, everything that goes with it, you have to do it within an ecosystem. So we are really trying to move the ecosystems and add this technology to ARM, to Intel, to RISC-V. And there is good reason why the industry has over the years sort of down-selected to just these few. Because, you know, they're sort of big and powerful. There's a huge amount being invested in them, and it's very hard to do anything different. There's been major software evaluation by academia and industry using the ARM Morello prototype, and a lot of software is now being ported over to this CHERI RISC-V platform. But that's really given us a lot of very useful data points. It's been fascinating out of the technology access program, seeing how many companies say, oh, that was a lot easier than we thought. You know, so those sort of things are really useful to know. And the other thing we're finding is companies are saying, oh, crikey, it's finding loads of bugs. So even if we can't yet buy the hardware, can we keep our Morello box? Because we want to test our software on it, because it's finding the bugs for us. I mean, ideally, they want to deploy using CHERI. But that I also find hugely reassuring. It's also really important that across these three architectures, ARM, Intel AMD, and RISC-V, that if you write software, that software will run on any of these. Okay, so their instruction sets are all very different, but from a programming language, even a low-level one like C, your C code should run on all of these, and when you're using CHERI features, it should run on all of these. You shouldn't need to modify your software. And that's also going to be an interesting thing with the CHERI Alliance to make sure that happens. And that's going to be another aspect of standardization. We're still sort of, there is some refinement to how we do CHERI. But I'd like to leave the message that, you know, all the core ideas at this point are really well baked. We really know how it works. All of the memory safety stuff, there's a huge amount of compiler support and so on. That's all really solid. Inevitably, there's always going to be things around the edges. And we see this, I mean, ARM and Intel and RISC-V continue to innovate, right? So even if we put CHERI out there, there will still be scope to innovate and advance the technology. But I think, you know, we're really confident now we have a very good base level understanding so that, you know, things can be deployed into product. So it's ready to be exploited. And one of the great things I think in this is a smaller space doing stuff on RISC-V is, you know, startup companies can get involved, ship product, and, you know, really innovate. And you know, I'm really hoping that we'll see great successes out of this. And then we'll see opportunities for the large established players to come and use the technology. But generally with the large established players, they're just rather risk averse. And so it's persuading them that you know, the benefits are worth it. And it's so difficult to quantify, I find. We've been talking about this in terms of, you know, the sort of cost-benefit analysis. And a lot of the big players are spending vast amounts of money fixing bugs, where we know if they had CHERI, it would just completely mitigate the problem. But it takes time for them to, you know, gain confidence in CHERI and really figure these things out for themselves, because at the end of the day, we can't really tell them. They have to sort of discover this stuff for themselves. And with that, I'll finish. Thank you very much.